This is lecture two. In lecture one, we went over pre-exercise screening, discussed the purpose of it, and talked about the potential consequences of not doing it, and went over the risk factors that associate with a higher chance of experiencing an adverse cardiovascular event, both the minor risks and major red flags. In this lecture, we'll be talking about these three things. So, a little bit about health in general, old and current definitions both. We'll talk about the goals of exercise prescription, and we'll cover some major principles of exercise physiology. Nothing too complicated, just foundational principles. So you and everyone you've ever met either has or has had a body, and maybe we have different parts here and there, not just because of catastrophic injury where a limb goes missing, but we could be born with different anatomy. There are supernumerary muscles. These are muscles that maybe you have that other people don't, or vice versa. So one example would be a palmaris longus tendon. You might be able to see that in your wrist if you pinch your thumb and pinky together, or you might not. There's more than 10% of people don't have that. I have one in my right limb, but not one in my left. So examples abound of anatomical differences. This is just one of them. But the point is, we all have bodies, and those bodies have a lot in common. Not everything, but they have a lot in common. And human physiology, as a field of study, investigates the functions of that body. So, like growth and development versus atrophy and degeneration. It investigates metabolism, the balance of anabolism and catabolism. It looks at how the body reacts to environmental stressors and other stimuli, and how different body systems interact with each other. The cardiovascular and pulmonary systems, for example, the interplay between those, and on and on and on. There are a million lines of inquiry for the physiologist. But the field didn't begin with complex questions about metabolism and adaptation and performance. For most of our history, we've been focused on surviving. Today's multifaceted definition of health is less than a century old. It was in the 1940s when the World Health Organization formalized a definition of health that wasn't dependent on disease. Our tendency before then was to define health by the absence or presence of a disease state, which makes sense. It makes sense to focus on disease and words like infirmity, given that life expectancy was a much larger threat to us up until relatively recently. When you look at life expectancy charts like this one, the 1940s seems like a reasonable time to begin focusing on some less painful, less scary, less mortal features of human health and well being. Through most of our history, though, people have been dying of all sorts of causes. I mean, including their teeth. Abscessed teeth didn't just compromise dining satisfaction, it could be lethal. But at least that was a cause of death with visible features. With most causes of death, if you didn't see the sword or the hatchet embedded in the body somewhere deep, it was probably a mystery why the person died. I mean, aside from the obvious symptoms we can see and feel, these diseases and infections, whether they're viral or bacterial, they were invisible to our ancestors. I mean, in a very real sense, our forebears were literally plagued by invisible monsters. And that's what I'm showing with this greenish diagram in the center of the screen. That's my drawing of HIV, which didn't emerge in the US until 1981. So this wasn't an epidemic of our oblivious ancestors. And you don't need to know anything about it. It just illustrates the complexity of disease that couldn't possibly have been understood in any capacity until recently. So in this particular diagram, there would be GP 120 at the end of the little bone looking arms, and that binds to a CD4 cell surface receptor. Reverse transcriptase and integrase are the little green and blue marbles in it. So this integrates itself into the host genome through reverse transcription. And those little millipede looking things, that's viral RNA. So you don't need to know any of that. This is just to say these little invisible monsters are complicated, and we're still learning about them. And we're still incredibly foolish about them, about all of them. We know profoundly little, but we continue to learn every year more and more about illness and disease. And as we do, we also learn about optimal human functioning. Health is a continuum, and as it turns out, elite human performance involves all of the same physiology. Uh, Now, physiology is a subdiscipline of biology. So, biology investigates essentially everything alive and everything about those living everythings. Physiology is a little bit narrower in its scope, and human physiology, especially, gives us a context for understanding. Maybe in a gen bio class, you're learning about cell division or signaling proteins or DNA repair or something like that. And as a student, it's reasonable to sit in that class wondering, where is this happening? Is this process happening in me? Is this something that's like in feces? Maybe it's a metabolic thing that yeast does, or are we like in bunnies, like the yeaster bunny? Where is this happening? And then getting into human physiology, and especially exercise physiology, being a subdiscipline of that, it helps to know that everything we discuss here, everything we'll discuss, is something your body is doing. So in this sense, the discipline, the field, it functions as a coat hanger. It's a context upon which we can hang physiological phenomena in a memorable way, a meaningful way, and often a prescriptive way. And on the subject of prescription, exercise physiology isn't just studying the body at rest. It looks at the responses of cells and tissues and organ systems when subjected to stress. I mean, there are infinity questions about health and our fitness and well-being that we can ask, but how do we answer them? I mean, sometimes people reason from past experience or traditions, or they adhere to superstitions or gut feelings. Maybe an authoritative figure has made a claim. Yeah, oh, this is what Dwayne Johnson does for his leg workout, or this is a supplement that an Olympic athlete swears by. And these things influence people, but science is far and away the most reputable influencer, and it should be the influencer that we all look to for answers to our ex-phys questions, to help us achieve our goals, whatever those goals are. So what are your goals? So think about your own goal. You must have some. You must have some goals. We're well past 1948. Our health goals tend to be much more complicated these days than just the absence of disease, but they still seem to fall into these four categories. There's physical appearance, what you look like in a mirror and selfies or whatever. There's athleticism and other expressions of human performance. There's general fitness and longevity. I want to age like Hugh Jackman or Cher or somebody. And then there's recuperation. There's healing from what ails us. Domains like physical therapy would fall into that goal. If all you care about is physical appearance, you can just Photoshop your pictures. That goal attainment should be easy if that's your only ambition in life. If all you care about is athletic performance, just bribe the refs. Goal attainment, it'll be costly, but otherwise it should be easy. Typically, though, our goals span multiple domains, and we care about them more than we let on. We want to live longer and run faster and look good doing it, and 100 other much more personal wishes that maybe we don't say out loud. And if we want to accomplish any of these, post 1948 ambitions, we're not going to get there with hunches and gym science and the wisdom of social media influencers. We need real science to accomplish those goals, to answer these questions and accomplish those goals. We need an understanding of exercise physiology. So let's talk about some basic principles. First up, organ systems, like the musculoskeletal system and neuroendocrine system. There are a lot more than what I've listed on this slide. These are some of the systems we'll talk about this semester. Less so cardiovascular and pulmonary. We'll touch on those, but we'll spend a lot of time on the other five. Now, with organ systems, we don't organize things according to regions. Like, here's everything that happens in your limbs. Here's everything that happens in your chest. Here's your southern hemisphere. Stuff that happens down there. Muscles and bones and ligaments and vasculature and tendons and cartilage and sweat glands and whatever, all in that quadrant. That's not how we structure the body's systems. We organize them according to function. Circulation is a function, or air exchange, immune function, nutrient absorption, the gastrointestinal system, and metabolism. We label these systems by their function. But there is interaction. There's a ton of interaction. We're not robots. On a computer, it's like, well, here's your word processor. That's 100% responsible for word processing. No investment from any other systems. And an internet browser is 100% responsible for internet browsing. Our biological systems all work together. I mean, pretty much all of them all the time. I mean, the immune system, for example, is critical in the response of your skeletal muscle tissue to exercise. And there's interplay between everything else too. Tons of interplay. Homeostasis, this is another principle. Your body maintains a really narrow window of physiologic ranges. I mean, if you just absorbed the temperature of the room you were in, the environment you were in, you die. If it's 70 degrees where you are and your body assumes that temperature, that's death. And we have these sliver thin ranges of blood gases and blood sugar and pH and circulating levels of all sorts of stuff. I mean, there are potentially catastrophic consequences if we go a little bit too high or a little bit too low. So, homeostasis is a self regulated biological stability or an equilibrium. And feedback loops, this is really how we manage our homeostasis. This interacts with homeostasis. So there are negative and positive feedback loops. Negative loops, this is what maintains our homeostasis. So think about temperature. Your body begins to accumulate heat. It will detect the increasing temperature, and then you'll sweat to start dissipating that heat. Or if you get cold, on the other end of that, if you get cold, you'll shiver to increase body temperature, to balance it, to stay in that homeostatic window. Or sugar. Think about sugar. If your blood glucose gets too high, you release insulin. If it's low, you release glucagon to maintain that sugar level in its normal, narrow, homeostatic range. And then there are also positive feedback loops. These aren't maintaining homeostasis. Here, a small stimulus induces a big one. Life works in this way. We can call it like the Paris Hilton effect. Popularity begets popularity, or the more money you have, the more money you can make. Life tends to work in something like positive feedback loops, but in physiology, these are much more rare. Negative feedback loops are the common one. But childbirth is a good example of a positive feedback loop where a little stretch in the uterine wall initiates a positive feedback loop to get the mother in expulsion mode. Blood clotting also involves positive feedback loop. And action potentials aren't really a positive feedback loop because there isn't a receptor that's detecting the stimulus and an effector that's amplifying the effect, but it behaves in a similar way in that a small stimulus, a little influx of sodium results in a huge influx of sodium, a huge depolarization. And so that's a good image to illustrate what a positive feedback loop is, how it behaves. It's just not a proper loop. The next principle would be steady state exercise. Uh, this describes a consistency of intensity. There's an elevated metabolic demand. You are exercising at steady state exercise. You're not doing interval training though. It's not up and down. There's no stop and go. It's steady in its pace. And at the onset of exercise, you'll probably be producing an excess of metabolic byproducts, but your body gradually accommodates the stress and regulates the state of your insides. Heart rate increases, breathing rate increases, you sweat, you buffer hydrogen ions, which means pH, which means acid. So despite the elevated workload, you find yourself operating within that homeostatic window. Um, again, you're not in a steady state internally. The instant that you push start on the treadmill, it takes time to arrive in that well-regulated state. But with repeated exposure, with repeated exercise sessions, the time required to reach a steady state should decrease. But you won't be able to accomplish that steady state during high intensity training where the demand for energy outstrips the supply. Your fuel sources would begin to decrease and byproducts would be accumulating. It has to be a moderate intensity to achieve this. Individuation, this is the next principle, which is basically individuality of the individual, and that's what individuation means. So are you an Olympic wrestler? Are you a Hulk Hogan kind of pro wrestler, a sumo wrestler, an arm wrestler? Maybe you're not a wrestler at all. There are important differences from person to person. You can't just prescribe the same therapy or diet or exercise or drug or anything else to everybody. uh, Now, what are some of the specific differences between people? There's variation in musculoskeletal architecture, height and limb length and origins and insertions of the muscles. Those muscle attachments, those really matter. Something we'll talk about later in this semester is a trade-off between speed and force production, speed and strength. Um, but there's also muscle fiber composition. So, how many total fibers do you have in a particular muscle? And what's the percentage of type 1 fibers versus type 2 fibers? If you want to be an Olympic sprinter, you better have a ton of type 2s. Whereas if you want to be an elite marathon runner, you need a ton of type 1s for that. There may be differences in tissue integrity owing to history of injury or prior training, maybe illness or age. If you've ever been injured before, that's really the biggest predictor of whether you'll be injured in the future for lots of reasons. We'll talk about those reasons in future lectures. There are also functional differences between people. Could be mechanical limitations like range of motion, or capacities in balance and coordination, something like that. There are differences between everybody in enzyme composition. Maybe one person has a higher density of mitochondrial enzymes and someone else has more glycolytic enzymes or whatever. Our metabolic reactions are carried out by enzymes, and concentrations affect those reactions. This matters a lot in terms of exercise tolerance and response. Big topic for later in the semester. There are hormonal differences, discrepancies in testosterone or estrogen, insulin, leptin, IGF, and so on. I mean, the obvious example is that men might have 15 or 20 times higher levels of testosterone than women, but women can be higher in growth hormone. And so there are differences in levels of hormones. And beyond that, there could be differences in metabolic health, or there might be cardiopulmonary conditions, maybe asthma or COPD, something like that. There are probably psychological differences, whether people admit it, on matters of goals and motivations or past associations with exercise and fitness. The point of this is that the differences between one body and the next are vast, and treating everyone the same is at least inappropriate, if not outright negligent. So we have to look at each individual as an individual, or we risk malpractice and the types of interventions we might suggest. Now, this one isn't a common principle. It's something I've been talking about for 15 years or so. And I've called it a lot of things throughout that time, testing out coinages like positive injury principle, things like that. But my tagline has stayed the same since I was in the student seat. And that slogan explains the principle well, which is exercise is good for you because it's bad for you. This is something we'll talk about more, but briefly, why is cardiovascular exercise good for the cardiovascular system? Why is it heart healthy? Because it's terrible for the cardiovascular system while you're doing it. It could kill you. So if your body is anticipating repeat bouts of that same stress, and if it wants to stay alive, it will adapt. And the same thing is true for other adaptations. Just look at the immune system and how that gets bolstered. So many things that are manageably bad for us will ultimately bolster our health. We could call this the "what doesn't kill you makes you stronger" principle, but it's a lot more complicated than that. That's way too crude to just accept as is. First, long bouts of endurance exercise will likely elicit a chronic lowering of your maximum voluntary contraction. They'll have a weakening effect. So that's not necessarily making you stronger in a literal sense. And there are other types of stress that maybe don't kill us, like the emotional turmoil of bullets nearly killing us that lead to PTSD. And it's hard to call that a strengthening effect. So we'll talk about this a lot more later. The major point to remember now is that exercise threatens us. And that's why our bodies remodel themselves to better withstand future bouts of that same stressor. Now, there are four principles here that are all related, which is habituation, sensitization, accommodation, and adaptation. We'll go deep into the details of these in the coming lectures, but a brief summary to hold us over until then is that these are similar but different bodily responses to better tolerate our environment. Now, sometimes we just tolerate it without change. If you're flying on a plane and you're seated next to a screaming infant, you do your best just to endure the unpleasantness until the flight is over. You don't adapt to that experience unless you do it day after day after day. Then you'll probably habituate, which means you won't be as sensitive to that stimulus. A better example of habituation is if you move next door to a dairy farm, at first it'll be punishing to your nose and your soul. But over time, eventually, you won't notice it anymore, hardly at all. That is habituation. Sensitization is the opposite. You become more sensitive. Like a musician, he becomes more keenly aware of an instrument's tuning. After playing for a couple of years, you can tell when a couple of strings are very slightly out of agreement, and you weren't capable of that as a beginner. Now, habituation and sensitization can fall under either accommodation or adaptation, depending on how the change in sensitivity works. But let's consider them as wholly separate from accommodation and adaptation. Accommodation is changes that are quick to arrive and just as quick to depart. Like being in a bright room or a dark room, your pupils change. It might take a couple of minutes to adjust, but unless you're leaving the ophthalmologist's office, the effect won't linger. It arrives and departs rapidly, relatively rapidly. Adaptation is what lingers. That takes time to occur and it takes time to pass. So if you do regular cardiovascular exercise for a few months, you'll increase your blood volume and your mitochondrial content and capillary density and so on. There's a lot of structural changes that take time to develop, different amounts of time. Blood volume changes pretty quickly, but they persist after exercise ceases for a while, not forever, but they persist for a while. That is adaptation. Now, this is another principle that we're going to cover in detail in coming lectures. And we'll add some other names to the roster of historical figures, Edward Adolph and stuff. But But today, uh, we'll be inducting two names into the Hall of Fame for specificity of adaptation, a major principle that's critical to our field. So Julius Wolfe and Henry Davis, these are the names we're inducting. Each has their own law, but both laws essentially say the same thing. If you apply a stress, the body remodels the stressed tissues according to the specific nature of that stress. For now, that's all you need to know about it. But details on this principle are coming soon. Thinking about adaptation in general, this is the dose response curve. In short, the larger the dose, the more calories burned, the more musculature stressed, the greater the response, the greater the adaptation. Now, this applies to both the individual workout and the summation of workouts, the accumulated adaptation over time. But in addition to the invest more, get more phenomenon, we also see diminishing returns with greater investments, too great of investments. If you're over investing, there are potential consequences, but we'll save that topic, overtraining, for the end of this lecture. The trainability principle. This is different from the dose response curve, and it's not describing an investment payoff response. It's describing the different journeys of different individuals. In the chart, there are 5 people represented: A, B, C, D, and E. These are 5 different people, and they're all responding to exercise or to training differently because of individuation. These are individuals. They respond to things differently. Let's just use a personal example and make it extreme. It doesn't matter how much I swim. Michael Phelps is going to beat me in the pool. It doesn't matter how much I lift. I'm not going to set a world record in the squat. It doesn't matter how much I cycle. I'm not going to win the Tour de France. We all adapt differently, even if the training program, the training stress is identically applied. We're all individuals. Now, the FIT principle, FITT, which stands for frequency, intensity, time, and type, these are the characteristics of an exercise program, some of the characteristics that influence the specificity of our adaptation. Our cells notice a lot more than FIT and T, but this is some of what matters. In the 9th edition of ACSM's guidelines for exercise testing and prescription, the acronym became FIT-VP, V for volume and P for progression. But volume is just a way of combining time and intensity and frequency. Um, those components to arrive at a total exercise product, with the idea that if you're short on time, you can increase intensity, vice versa. And progression attempts to define changes in a program over time. For the sake of this class, ignore those, ignore V and P, and just know F, I, T, and T, the frequency, intensity, time or duration, and type or mode of exercise. And very generally, we can think of intensity as especially important in the dose response results. The higher the intensity of exercise, the more cells and tissues and organ systems are recruited, the more stress they endure, the more threat they experience. And accordingly, if it doesn't kill you, the more adaptation they should theoretically undergo. Now, how we measure intensity also matters. There are absolute measurements of intensity and relative measurements of intensity. So thinking about the FIT principle, the last T is type, exercise type, so like biking, for example, or swimming or playing basketball and so on. From this perspective, a casual bike ride and an all-out Wingate intensity ride are similar. The type is kind of the same thing, but where they differ profoundly is in intensity, the I of the FIT principle. So if we were to tell an NBA player and that player's grandmother both to run at 10 miles per hour, that's an absolute measurement of intensity that is preserved across both of them. If we were to tell them to bench press 100 pounds, that's an absolute measurement of intensity preserved across both. But if we say, exercise at 50% of your VO2 max, they're going to be doing very different activities. They'll both be exercising at the exact same intensity that was prescribed to them, which is relative to them. And that makes it a relative measurement of intensity. Another absolute measurement of intensity would be heart rate. Get on the treadmill and get your heart up to 100 beats per minute. The treadmill will be working really hard for the NBA player. But this grandma might get to 100 at a slow walk. Um, and so what we're looking at is differences in absolute values. Bench press 100 pounds, get your heart to 100 beats per minute, something like that. And relative values, run at 50% of your maximum speed, something like that. Now, the progressive overload principle is similar to some of these other notions of adaptation we've been talking about here. The amount of stress or load applied to your tissues must exceed a threshold to result in adaptation. And with training, the threshold will get higher and higher and higher. In an athlete, for example, gardening is not considered exercise, or picking up the house or vacuuming or whatever. This is physical activity, but for an athlete, it's not exercise. For an 80-year-old, mostly sedentary grandparent, mowing the lawn or going on a neighborhood walk probably is considered exercise. It crosses that exertional threshold. Physical activity, as matters of definition here, physical activity is pretty much any kind of movement that expends energy. But exercise is structured, it's typically planned and repetitive, and most importantly, is done for the purpose of improving physical fitness. It's done for the purpose of inducing positive adaptation. And to do that, to induce adaptation, the amount of stress has to be high enough. And the more we adapt, the higher that threshold becomes. So for the gardening, let's say it's a grandma, for the gardening grandma, mowing a small yard will suffice as exercise at first, but she'll adapt. And after a few sessions, the same stressor won't be sufficient to elicit further adaptation. She'll have to start mowing larger and larger yards, or mow even faster and faster, or add some hills, increase the stress somehow. But she'll adapt to that too. So for her to keep adapting, she'll have to make it progressively harder, add another acre, make it even hillier, start pushing the mower in a full sprint. That is progressive overload. As we adapt to the current exercise conditions, we have to continue to increase the challenge. Or even just some small part of the challenge, if you want to continue to make progress. The principle is most commonly, clichédly illustrated with Milo of Croton. He was a wrestler from 6th century BC, lived in Croton, which is a Greek colony in southern Italy. Now, Milo did two fictional things. First, he saved the life of Pythagoras so we could have his equation, right? A squared plus b squared equals c squared. He held up the roof of a falling building so that math could be advanced. And then second, and relevant to progressive overload, he hoisted a baby calf on his back and carried it until it became a bull. So he would progressively increase the stress endured by his bones and his muscles. So that's a good example of the principle. But so is lawn mowing, and lawn mowing doesn't involve the creepy tormenting of an animal. Um, so Now it's important to know that you can't just endure more and more intense stress forever and ever without a break. While progressively overloading our tissues, we need to unload them at times. Just occasionally, we need a break. So, in this sense, an effective exercise program resembles a bull market, not Milo carrying a bull, but the stock market. It has an upward trend, but there are some bear market periods. There are some periods where it goes down, or comparatively, hike Mount Everest. You can't just go up, 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 up all the way to the top. I mean, unless you have some oxygen, some really good Sherpas, you go up some and then down a little bit to rest, and then up some more, and then down a little bit to rest for another bout of recovery, and then up some more and down a tiny bit again, and so on. That's progressive overload in the way that it should be enacted. It shouldn't be interpreted as a constant, linear, unrelenting increase in stress. Otherwise, you won't recover. Which brings us to recovery optimization, another principle. If we want to recover between episodes of exertion, we need to consider these things, or we won't perform optimally in the next bout, and we probably won't improve as much as we could. And there are tons of variables, lots of variables that matter. Now, some of it is uncontrollable, genetics, biological sex, age, things like this, but lots of factors are controllable, like the fit characteristics. What are you doing for your exercise? Frequency, intensity, time, and type of your exercise, or conditioning level of the subject of the exerciser. What's their history of exercise? The environment you're performing in matters, the temperature, elevation, things like that. The amount of sleep you're getting is critical to recovery. Nutritional status matters a great deal. Hydration, medications, possibly, depending on what's being taken. So there are lots of variables that can affect our recovery between exercise sessions. And as an extension of recovery optimization, we have overreaching and overtraining. These are very different. Let's start with a normal exercise response. In the upper graph, that's a healthy exercise pattern. Each arrow represents a bout of exertion, an exercise session, and then performance will subsequently be depleted. It might last a day, it might last a couple of days. It depends on all those recovery optimization variables we just talked about. But soon, your performance will be better than it was before exercise, providing you did exercise correctly. And that's when you exercise again, and the same thing happens, right? You deplete yourself a little bit, your performance tanks for a short duration. Wait until you recover and then exercise again. Eventually, you'll be noticeably better at whatever it is you're doing if you follow that pattern. In the graph below that, in the lower graph, we have functional overreaching. Functional overreaching. You exercise, deplete yourself, don't recover fully. You don't wait long enough to recover, and then you exercise again. Don't recover from that one. Don't wait long enough, let alone recover from the first one, and then exercise again and again and again. It doesn't take too long to dig yourself into a hole a little bit, but just take a few days off, a few days, maybe a week off, something like that, and recover, and you'll rebound. You'll rebound really well. That is functional overreaching. You still emerge better than you were before. Non-functional overreaching lacks the rebound. Performance degrades, and there's some physiological maladaptation with no desirable adaptations. There are desirable adaptations to functional overreaching. There are not desirable adaptations to non-functional overreaching. Now, following a period of rest, you do recover, but it probably takes some weeks to do the recovery and to get back to your baseline. Depending on severity, it could even be months. It depends how hard you've pushed yourself, along with those recovery optimization variables we talked about: diet, sleep, hydration, medications, that kind of stuff. But functional and non-functional overreaching are both well observed in resistance training and strength sports. But true overtraining syndrome, this tends to arise from settings of chronic aerobic stress, like marathons and triathlons, where people are training maybe 4 to 6 hours a day. And there might be other compounding stresses along with the relentless physical stress. But overtraining syndrome is not like overreaching. It's a complex syndrome that you might never recover from. It's going to take a really long time if you ever do, but potentially you'll never recover from this. It involves lots of body systems, immune system, neuroendocrine system. Yeah, all these are compromised. Now, a lot of researchers will divide overtraining syndrome into two categories: sympathetic and parasympathetic. People who experience sympathetic overtraining would have increased heart rate and blood pressure, and they'd feel agitated and restless, whereas parasympathetic overtraining syndrome associates with a lower resting heart rate, and people tend to be apathetic and depressed. Now, this parasympathetic presentation is observed a lot more commonly in aerobic athletes. But the reality is, it's more complex than just having one branch of the nervous system predominating, sympathetic or parasympathetic. Sympathetic. I mean, there's so many complications that arise. I mean, we see tissue and bone injuries happening more commonly. There's extreme insomnia, extreme weight loss, adrenal insufficiency, cortisol might be chronically elevated, and so decreased resistance to infections and illness. You'll see systemic inflammation, decreased IGF, insulin-like growth factor secretion, sex hormone secretion is decreased, bone loss, glucose regulation is impaired. There's so many complications. Now, people don't experience every single one of them usually, but there's a constellation of complications that people experience, and as Larry Armstrong calls it in this article, it is a complex systems phenomenon. Moving on to periodization. This is a popular way that athletes and other highly structured exercisers try to maximize their goal attainment while avoiding performance detriments associated with non-functional overreaching or something worse than that. Common folk, right? Us casual exercisers, we don't need to get this detailed in our programming, but it's helpful for competitive athletes because athletes have different phases of the year owing to the annual calendar of the sport. Now, sometimes like an Olympic athlete might have a 4-year calendar, but in general, most people have a 1-year calendar in which there's a preseason, a competitive season, a post-season, an off-season. And if they just do the exact same thing year round, if they exercise in the exact same way during preseason as they do postseason, they're at risk of undertraining in some phases, overreaching, maybe overtraining in others. And plus, their goals are likely to differ, to be different depending on the time of year. So they modify their exercise program throughout the year to accommodate those things. So we break up the entire year as a macro cycle. That's our annual phase, as a macro cycle, and then within a whole year long macro cycle, there are probably a dozen or so mesocycles. It might be a month long each, maybe 6 weeks, something like that. Um, and in each one of these mesocycles, a specific goal is emphasized. And then within a mesocycle, there are probably 4, maybe 5 or 6 microcycles. Generally, this lasts a week. On Monday, I do this. On Tuesday, I do that. Wednesday, I take off. On Thursday and Friday and Saturday, I do these things. Sunday, I take off. And then repeat on Monday, repeat that microcycle on Monday, and I'll go through 4 microcycles, and that's a month, and that's my mesocycle is complete. Time to switch. So again, maybe a dozen mesocycles and the year is up. Now, nonlinear periodization it involves more diverse goal orientation. It's not just a classic like bulk up time, and then slender down time, and then plyometrics time, and then speed time and reaction time. or whatever. It's more varied than that with nonlinear periodization. But this is where we'll end. There are 1,000 more principles of exercise physiology, but this is a decent roster of the fundamentals plus my coinage. Now, size principle, that last one in blue at the bottom right, this is my favorite of all of them. And we'll get into this in exhausting detail soon, but not until we go through the structure and function of skeletal muscle and the neuromuscular system. Those are up next, but that's all for today, and I will see you in lecture 3.